Hi, so this is a continuation to the in-class discussion regarding homework question 3.3. In this example, we're trying to solve for the parameters of this circuit. We're trying to solve for the current passing at this inductor, so we'll call it IL. We know that IL, since this is a parallel RLC circuit, it will have a certain format. It will have, so IL, final result will be I final or I forced, I think they might be the same thing, plus I natural or I steady state or I natural. So it's summation of two results. Let's call it natural better. Because final usually comes with natural. So this result where I natural has a certain shape, has a certain formula based on this table in your book in chapter 9.1, depending on the relationship between alpha and omega node, where alpha, where damping factor alpha is equal to 1 over 2 RC and omega node resonance frequency. Omega node is equal to 1 over root LC. So you start by solving for those two values. For example, in this example, it will be underdamped. So this will be our this will be our function. Let's try to prove it out. Or it might be something else. You should solve and check. So assuming this is the function for I, the next step is to find the initial and final parameters or final initial and final currents for this circuit. So you will take the circuit here. Let's take our circuit and you find the initial and final conditions. So initial conditions, so initially an inductor will be an open circuit, while a capacitor is not charged, so it will be a short circuit. This means that for the inductor IL, it's an open circuit, so no current is passing. So IL 0 negative is equal to 0, and I and VL 0 negative. So all of the current is passing here, and we are measuring the voltage across those two nodes, so it's equal to 0 as well. While IC 0 negative is equal to all of the current is passing in this direction. But remember, our voltage at 0 negative is 0. Our voltage is a unit function. So all of so our current is voltage over V over R. And V is 0 over 1, which is equal to 0 volt. That's a long way to go around to proving that it's 0. While our VC is equals to in the initial conditions is 0 because it's they are connected. It's a short equals to 0. So everything is equal to 0. This is something we missed during the in-class discussion. Let's take the circuit and solve the final condition. So, and sometimes you don't need the final condition, but in this example, we found that we need more results. So the final condition after, like, since this is a DC volt, the final condition will be like fixed values. So after like an extended time has passed, the opposite will happen. Our capacitor will be fully charged by DC. So this will be open while our inductor is short. So this means that IL infinity, all of the current is passing in this direction. None of it is passing here. So is equals to Vs infinity over 1. None, none of the current will pass in this. All of it will go for the short over 1, which is Vs infinity, which is 10, while VL infinity is equal connected, so it's equal to 0. IC infinity current across an open nodes is equals to 0, while VC infinity is equal to 0. So currently we have some initial and final conditions we can use in our circuit. Let's start by defining our I. So we mentioned that IL is equals to IL of T, it's equal to IL infinity, which is the final response, plus the natural response, which is 10 plus e to the power negative alpha. I think I forgot this is the part we forgot during our in-class discussion. B1 cosine omega d of t plus b of 2 sine omega d of t, where d is omega node squared minus alpha squared. This is assuming you did solve for alpha and omega. Right now you can substitute for IL of 0. So you have one equation and get the derivative. So DL, derivative of DIL, IL of t over dt equals, and substitute at 0, get the second equation. So DIL of t over dt equals, we know what DIL of 0, we know IL of 0, which is IL of 0, which is 0, because current cannot cannot from 0 negative to 0 positive, cannot change drastically. So IL 0 as well as 0. What about DIL? Oh, what the derivation of the current? What's the derivation of the current? If you remember that, uh, the current across a capacitor, or the current across the voltage across an inductor. So V inductor equals L di L of t over dt. Yeah, so this is the equation for the voltage across the inductor. And we do have the voltage across the inductor, but we need to do some changes. We need to VL over L of 0. We do have this part equals the derivation of this. So now you have two equations and two unknown variables. Can easily get those two variables. Finally, you will have IL of t. Then you drive IL of t again. So DIL of t over dt over dt, not the function of t, over dt. So this will be our IL of t will be our first function, while DIL of t over dt, which is equals to VL over L. So from it, you can solve for VL, which is equals to VC, which equals to VR. So assuming that you got IL and VL, so power L equals IL times VL. I think that's it. And since you're not using the phasor format, it's just direct multiplication. You should get an answer. And in problem 4, you'll be checking for this answer using LT Spice. Let's make another quick video regarding using LT Spice for problem 4. So that's it.